In this video, I want to show the result of a recursive function to solve for a factorial of an unsigned integer. The second code segment is going to strategically print out values to show the recursive trace. Then I'm going to show animations that show the recursive trace going through the code, and then I'm going to show how this code is implemented on the instruction stack. So first, I have function unsigned int factorial that takes in an unsigned integer, and when I hit the base case, it returns 1. Otherwise, I return the factorial of I minus 1 times I as its recursive call. So initially what I have is unsigned int 5, and then I call the function factorial. So now when I run it, now you see that's already run down there, but I'm going to run it again. You'll see that it'll produce 120. So we know that 5 factorial is 120, and it gives us the correct result. But now let's take a look at a second code segment that produces a recursive trace. So just like before, I have unsigned int 5, but now instead of just printing factorial, I store the result of the recursive function in an unsigned integer. So when I call factorial 5, I'm going to print out the recursive call for the initial value. If we go into the base case, what we're going to see is I'm going to print out, it says base case reached, return 1, and then it will actually return 1. Then I'm going to store the result of what's returned in factorial I minus 1. And I'm going to print out at I, which is the level here, factorial I minus 1 returned, and that's going to print out the result of that unsigned integer. And then I'm going to return I times returned to actually return the actual value that we want. Then in main, it's going to say in main factorial, and it's going to print out the initial value here, is going to be equal to the result that's stored. So let me run this, and then I'm going to walk you through what's produced on the output. So initially, the recursive call for 5 is what happens when we get here, recursive call for I. So we're going to see that it goes 5, 4, 3, 2, 1, and 0 because it doesn't hit the base case. When it hits the base case, you're going to see that it says recursive call for 0, and then it says cout base case reached, return 1. So then when we hit the next case, that's going to be 1 here, and it's going to say at I equals 1, factorial I minus 1 returned 1. So now it's 1 times 1. Now it goes up to the next level, and then it becomes 2 times 1, which is why it says here. Then it returns 2. So 3 times 2 returns 6. 6 times 4 returns 24. 24 times 5 is going to return 120. So in main, we're going to see that we get the 120. So we can confirm that's correct. Now to show you an example of a recursive trace if you're writing it out, we see that we start with 5. And just like before, we're getting ready to set up the factorial calls. When we get to I equals 0, we hit our base case and it returns 1. Then 1 times 1 returns 1. 2 times 1 is going to return 2. 3 times 2 is going to return 6. 4 times 24 is going to 4 times 6 is going to return 24. Then 5 times 24 is going to return 120. The last thing I want to show you in this video is how this is implemented with the instruction stack and the registers. Every time we make a call to a function, we put a copy of that code on the instruction stack. So first we would start with main. Then we have a stack pointer that indicates which function we're actually running. That is the program counter in the Harvard architecture. Next, what I'm going to do is I'm going to call factorial 3. And what's going to happen is it's going to put a copy of factorial onto the instruction stack, and it's going to create 2 registers. The first register is the value that's being passed. So here num is here, and then I have a value that I'm going to want to return eventually. We don't hit the base case, so now it's going to call factorial I minus 1, which means it's now going to put another copy of the code onto the instruction stack. But now we see that how we have another register for the input as well as a register that we're going to use to return. Again, we don't hit our base case because num is equal to 2. Do the same thing. Num is equal to 1. And now, in this call, we have num is equal to 0. So what's going to happen is I is equal to 0, and it's going to return 1. What we're going to see is that we now create a return that's now going to set this value equal to F3 return. And now you're going to see this code popped off of the stack and the register is freed. So now we have 1 times 1, which is 1, and it's going to set that up to the next recursive call. It's going to do the same thing here, 2 times 1, and now it's going to do 3 times 2. So that means at the end, we have our factorial, 3 factorial returns 6.